Do you see that in full screen?
Looks very good.
Okay, great. So I'll get started, and yeah, hopefully there'll be some time at the end for questions if anything is on your mind, but I'll try to get through some material first. So yeah, thank you for that introduction. As you said, Akselos. I'm the co-founder and chief scientific officer of Akselos, and we're a simulation technology company. We're a spin-off from MIT, as was mentioned. And yeah, today we work with large industry, particularly the energy industry, but all kinds of different applications, offshore wind, offshore structures, petrochemical equipment, high temperature, high pressure, all kinds of structural things. And we really do focus on the structural side. And what we do is we provide what we call digital twins, which I'll say a little bit more about in this talk. But what we mean by that is a high fidelity computational replica of a physical asset. So you've got your physical asset and you've got your computational replica of it, which we call a digital twin. And the point of it is that that it's very high fidelity, so that it really earns the name twin by matching closely the physical asset. But also, it's not just a one-off simulation, like a one-off assessment you might do at design time. It's really tracking the asset through time, monitoring the asset through time. So it's not just a one-off analysis, as was traditionally maybe the mainstay of finite element analysis was the design type of workflows. We're trying to bring it into the operations. That's really our focus, is bringing simulation technology into operations, so it's tracking assets and helping operators manage their assets in a smarter, more efficient way. So I'll go through some of those ideas in this talk. And you can see from the title, what I'm referring to here is component-based reduced order modeling. So we have a specific approach, unique approach. We refer to it as RBFEA, but really that's a component-based reduced order modeling approach, and we apply it to large-scale industrial digital twins. So here are some pictures of different kinds of assets we've worked with. As I've mentioned, these are kind of petrochemical type of assets, including nonlinear effects like creep over here, and various kinds of plasticity come up. Because I know this is a nonlinear FEA class, you'd be interested in that kind of thing. And also offshore structures. So these are very, very large structures, and that's where the component-based reduced order modeling comes in. It enables us to model these gigantic structures. This one here is, for example, 3 times as big as an aircraft carrier, but we're modeling in very high fidelity through this approach. And if I keep moving, as I mentioned, at the end of the day, our customers are not, what they're interested in is maintaining and managing their high-value assets in a smarter and more efficient way. So what we typically deliver to our customers is not a very complicated model. That's what we develop under the hood. But at the end of the day, what we give to our users, so what we put in their hands is more like what you see here, a dashboard. Because the point of a dashboard is it summarizes all the relevant information about their asset and gives them useful, key performance indicators, KPIs, that help them understand their asset, help them do their job better. So I think that's an interesting distinction, again, from the traditional FEA world, which was, putting very complicated tools in the hands of PhD people who are doing R&D design type of stuff. We're kind of working on the other end, which is putting the tools in the hands of operators who just want to manage their asset better. They're dealing with the steel of their asset. They want to manage it better. And under the hood is all that very complicated computational modeling. That's all necessary. That all has to be done. Everything you've learned in this class, that kind of stuff needs to be done. But that is, in some sense, hidden from the users that we mostly interact with. The users that are getting value out of our solution don't want to see all that detail. They want to see the outputs of the model, which are things like, remaining life, where are the fatigue hotspots, if you incorporate a new defect into the model, is it going to be an issue or not? These kinds of simple to understand outcomes that can be summarized in these kinds of dynamic dashboards that you see here. So yeah, this is just to give you a flavor of what we the value we bring to our customers is through this kind of tool, but under the hood is all the heavy duty computational modeling stuff. So yeah, again, just to summarize what Akselos, the way we interact with our customers is we present our solution as what we call structural performance management. So we see this as tying together of these two things: operational excellence and asset integrity management. So there's traditionally been a lot of focus in the industry on operational excellence. So that's tools like monitoring simple flow rates and things like that, and ensuring that the process in, for example, a plant is operating at maximum capacity. But there was traditionally not really much focus at all on asset integrity management during operations. It was more done at one-off studies and things like that. Our mission is to put these two together, and that's what we call structural performance management. And then that gives these kinds of outcomes: enhancing asset performance, ensuring uninterrupted operations, and extending asset life. So that's how our customers get value from Akselos. They are able to deploy this solution, bring asset integrity management into operations, and get maximum output from their assets for the longest possible time. So that's, and this is just a little bit about the company. We have offices in various places around the world, and we work with a lot of large companies delivering this structural performance management solution. So that's just a little bit about the commercial side to give you some context. But then now, if we get into the more technical side of things, what exactly are we delivering to our customers? So as I've said already, we talk about delivering digital twins. So that's a term you may have heard. A lot of people talk about digital twin in a lot of different contexts. So because of that, I like to start with a definition of what a digital twin is. This is not my definition. This comes from the US National Academy's report on digital twins from 2023. And I'll just read it out because I think it's a helpful starting point for this discussion. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural, engineered, or social system or system of systems, is dynamically updated with data from its physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So actually, this is a very accurate definition in terms of what Akselos works on, because we have, as I mentioned, high fidelity models, which reproduce the physical twin accurately. So that's where the predictive capability comes in. We believe there's nothing more predictive than a physics-based model, based on first principles of physics, for example, like FEA type models. Dynamically updated, that's referring to what I've already talked about, bringing inspection data in or sensor data in from an asset and updating it. And the bidirectionality, and of course, realizing value. I mean, that's all that structural performance management stuff I was talking about is 100% focused on realizing value. And the bidirectional interaction is that, the digital twin informs the operator, who will change the way they operate, and then the data flow will go, sensors and things related to how the operation has changed will flow back to the digital twin. So there's data flowing both ways in this scenario. So I think that's a very good definition that really captures the essence of, at least the way I see a digital twin. And so that's kind of the way we think about digital twins at Akselos. And so what does it mean to deliver that to a customer? Well, just to give a little bit more focus on the way we do it, as I've already said, our digital twins are used in operations. They incorporate all available data, which includes design data. If you're going to do a physics-based FEA type model, you've got to start with a design. So that can be things like drawings, engineering drawings, CAD, whatever is available. If the asset is old, it can be very old data, but we work with whatever is available. So design data helps you set the model up in the first place, and then operational data like sensor feeds, inspection reports, etc., give you that dynamic updating. So every time you got new data from the asset, the model can update and then reanalyze and ultimately deliver value to operators. Our focus, as I've already said, is to model entire assets in full 3D and include the as-is condition. So have automated ways to update the model to incorporate whatever new data is available. And high fidelity modeling ensures that you're able to capture the true as-is condition. And a key part about why reduced order modeling comes into the picture is the analysis must be fast enough to keep up with the cadence of operations. So a lot of times you get sensor feeds coming, every minute, every 30 seconds. New data comes every 30 seconds, and you have to have a fast solver to keep up with that cadence of the data feed, especially if the model is very large, right? So we're typically dealing with very large models and fast data feeds. So of course you have to have a very fast way to solve these models while still being reliable to be predictive, and that's where reduced order modeling comes in, physics-based reduced order modeling, which is what we do. And the fourth point here is we really have to be industry standard compliant. So there's all sorts of industry standards. I mean, this really touches on that. In the intro, we discussed being practical applications of FEA. So something I never really dealt with when I was on the more academic side of things was all the industry standards. But once you get into industry, you see that everything is is guided by standards. Whenever someone does any kind of analysis or report, it has to be conforming to the industry standards because of legal compliance reasons and so on. So, we've spent a lot of effort making sure all our implementations are industry standard. And with our reduced order modeling approach, it builds on top of conventional FEA. So all these standards are all built around FEA, finite element method. And because our RBFEA approach, as I'll talk about shortly, builds directly on FEA, our approach is also industry standard compliant. So that's one very powerful thing, and that I'll talk about shortly. But that is actually a very strong contrast with things like machine learning methods, which are not compliant with industry standards. So you have a very hard time deploying those kinds of non-physics-based methods in mission-critical situations. So a little bit more about how we actually achieve this. I've already alluded to this, but the way we achieve these goals is through reduced order modeling. So we use physics-based reduced order models, or some people use the term scientific machine learning, as which I'll talk about shortly. Maybe the comparison and contrast between reduced order model and scientific machine learning. In my opinion, they're very, very closely related, so I kind of use them interchangeably. But yeah, Akselos uses physics-based reduced order models / scientific machine learning, and specifically RBFEA, reduced basis FEA, to achieve these goals. And the way we do it is, well, the way this works is we have the reduced basis method, again, which I'll talk more about shortly. That's a reduced order model, which provides fast response to keep up with operations. We've already talked about the importance of that. Component-based. So I gather this class has talked about, substructuring. That's one type of component-based modeling. We also use component-based modeling to enable large-scale detailed modeling of entire assets. When you combine it with these things, it's also parametric. So we're able to incorporate new data based on sensor or inspections, and, for example, run what-if scenarios. So parameters means you can change things like temperature, strain, load, defects, and reanalyze efficiently as part of the reduced order model. And also we have accuracy guarantees, accuracy indicators, because we have what we call a posteriori error estimators. So when you run your RBFEA solve, and it gives you an error estimator which ensures accuracy within a certain tolerance level compared to FEA. So again, this is very important for the compliance with industry standards. So putting all these things together is what really powers our physics-based digital twin solution. So again, this is a topic that I get asked about a lot. How does what Akselos does compare to machine learning or scientific machine learning? So I made this slide to address that question. Here's my view of how the map can be laid out. So in my view, reduced basis method is, which again I'll talk about shortly. Maybe it's a bit premature because maybe some of the audience doesn't know exactly what I mean by reduced basis method, but I'll talk about that in a bit more detail shortly. But a reduced basis method, in my view, can be considered physics-based scientific machine learning, because what you do is you have a training phase based on physics to learn the response, and then you have a fast online evaluation phase. And that's really the hallmark of machine learning. You have a training phase, which can be very compute intensive, where you're using data, and then you have an evaluation phase, which is fast typically. And so, here's some type of scientific machine learning methods in the green bubble, and some reduced order modeling methods in the blue bubble. And you can see there's obviously strong overlap here. There's also some stuff, pure neural network methods you might not consider reduced order model because they don't have the physics aspect to them. But, and response surfaces similarly, they're not really reduced order models in the traditional sense. But, there's a lot of overlap here, and it can be up to different people might classify things differently. But this is just one way you could lay it out. And you can see here, reduced basis is the focus of today's talk. You see that in the intersection here. So I would consider that kind of a foot in each camp. All right, so now on to the reduced basis method. I don't have a ton of time to go through all the details here. And of course, you can, if you're interested in these topics, there's a lot of literature. So as was mentioned at the beginning, I joined a research group of Professor Patter at MIT. So he's really one of the founding figures of the reduced basis method. And there's plenty of there's hundreds of papers on the reduced basis method if you want to look them up. But here's one review article, from a while ago, which gives a good overview of some of the key ideas. And so if you want more details, you could look that up as a starting point. But yeah, I just want to give an overview of some of the key ideas. So let me start with FEA. This is a way you could write a weak formulation of the finite element method. If you've got a bilinear form and a load operator on some function space, you could formulate finite element as find the given the parameter vector mu. So mu is a parameter vector which defines things like material properties or whatever, like I talked about earlier. You want to find the solution that satisfies the PDE weak form for all test functions. So that's a typical way to write a finite element method, right? You're trying to find the trial function that satisfies this weak form for all test functions, okay? Now, the reason I wrote that out is because down below is RB, reduced basis. You can see it's exactly the same as FEA. The only difference is the space, the discrete space you're looking in is different. It's much lower dimension. But when I say reduced basis is based on FEA, this is what I mean. It's exactly the same formulation. You're just looking in a different space. You're looking at a reduced space with a reduced basis, with a reduced set of basis functions. So instead of the traditional polynomial hat functions on tetrahedra or parallelepipeds or whatever, you have a reduced basis, which is much lower dimension. Little n is much lower dimension than big N, but the formulation itself is identical. So that gives you a lot of power because you can really relate this solution, this formulation to this one. That's what enables you to do error estimators and things like that. And it also is what enables us to say that RBFEA, builds on FEA and is also industry standards compliant because the formulation is identical. You're just using a specific set of a reduced set of basis functions. And it's often helpful for people to see this in a more matrix vector type of formulation. So how does this look in matrix vector formulation? Well, in the FEA formulation, it looks like this. You've got a stiffness matrix of size n, capital N by capital N, big N by big N. You've got a load vector and solution vector of length big N. So you get this simple linear system here. In the case of linear, this methodology also applies for nonlinear, but I will not have time to go into that today. But you can get the idea that the same kinds of ideas will apply in nonlinear. Again, it would be the same. You'd have a nonlinear PDE here, and the only difference is you would have a little n instead of a big N for the nonlinear formulation of RB. So again, same idea applies to linear and nonlinear, but let me just address the linear case here today. So yeah, we have this finite element formulation. Well, what does the RB one look like? Well, actually, it's you put your reduced basis in this z vector, which is a rectangular vector, and then your formulation you have this z transpose az to basically change basis into the reduced basis, right? So now your solution vector is only little n because you've got this z change of basis operator here, which comes into the system. So you can see in terms of linear algebra, it's very natural formulation, z transpose az and z transpose f, but everything else is the same. So yeah, that's hopefully giving an idea of what we mean by reduced basis method. It's really just a change of basis to a reduced set of basis functions. And the tricky part is not this. The tricky part is, well, what are the basis functions? You have to have a good way to pick these basis functions so that they are representative of the solutions you're trying to reproduce over the parameter range you're interested in. So let me just say a little bit more about parameters. The whole point about parameters, well, if you didn't have parameters, you would just solve this problem once and that would be it, right? But if you've got parameters, then every time you change the parameter, you have a new stiffness matrix, you have a new load vector, you have to solve the problem again, right? If you have thousands of different versions of the problem you want to solve, because in operations you're getting new data every 5 seconds, or in a design study, you're trying to loop over all the different design parameter space, then you're going to have to solve the problem many times. And so that's where parameters come into the picture. So you can see a temperature as a parameter. You can see thickness of these stiffeners as a parameter. You can see a geometric parameter, which is the angle of this conveyor belt. You can see loads as a parameter, which are wave loads on this floating offshore platform. So you can have all kinds of different parameters. And that's really what brings a lot of power to the methodology, because if we can make sure we have a reduced basis that's good for all the parameters you might be interested in, then you can solve the problem quickly for any parameter, not just solving it once. If you just solved it once, as I said, you would just solve it once with FEA and be done. So how does that work? Well, if you think about parameters and you think about your solution, for any parameter vector mu, what you really have is a point if I go back to the FEA solution, for this, for any, if you give me a parameter vector mu and I solve this problem for that parameter vector mu, I'll get a particular solution vector in this space R big N, right? So you can think of that as for any particular mu, I get a point in this high dimensional finite element space, x big N. If I change mu, I'll get a new point. If I change mu again, I get a new point, right? So it's like you're mapping out a path in this high dimensional space where the space is is of dimension big N, right? Because every solution coefficient, because the solution vector has big N coefficients. So obviously you're in this big N dimensional space. It's completely impossible to visualize this, but conceptually you can imagine that it's a low dimensional manifold as you sweep through your choices of parameter vector mu. So the point then is that the parameterized this curve here, you could call it a solution manifold, right? As you change mu, you're getting this manifold in this space here in a high dimensional space. And the point is that this is actually what we care about. This is all of the solution content that we care about. We don't care about the high dimensional space per se. And actually, an FEA method you can see as being quite inefficient because the FEA approximation represents everything in this high dimensional space equally well. That's what an FEA basis does. It doesn't care where you are in the space. It represents something way off this solution manifold just as well as something on this solution manifold. Of course, that's the great thing about FEA. You don't have to worry about, where your solution is. It'll compute the solution. But if you're in a situation like a digital twin and you know what your asset is and you know the types of inputs you can expect because you've run the thing for a year and you want to run it for another year, you don't need that power. You don't need this generic approximation capability of FEA. What you want is to focus in on the solution manifold you care about and approximate that very efficiently. So that's why we do this in the digital twin context. It allows us to be very efficient because we don't need the ability to approximate any solution in this high dimensional space. We want to focus on the ones on the solution manifold. And so what do you do with RB? Well, you take snapshots. That means you solve the PDE with FEA or whatever full order method you have to compute the actual solutions on this manifold. And that gives you snapshots on the solution manifold. And then you can use those snapshots as your basis. Okay. So that's a simple idea, but it's very powerful. If you take snapshots on your solution manifold and use them as your basis, you now have a representation of this solution manifold that's not completely generic. It's now very targeted at this solution manifold. So that's the key idea. We generate a subspace that's highly targeted to the solution manifold via snapshots. And so there's two paths to reduce basis then. One is to compute the snapshots, for example, at evenly spaced parameters, and then you apply the SVD to get a compressed reduced basis. That's what people call the POD method. That requires a full order solve for each parameter sample, so that can be problematic. The other method, which is more the focus of Professor Patter's group, has been the greedy algorithm, which where you basically greedily select the new parameter. And the nice thing about that is if your reduced basis will end up only with 20 basis functions, you actually only do 20 full order solves for those snapshots. Whereas with a POD method, you might have to do 500 full order solves, and then you compress it down to 20. So that's the kind of difference. And so what does the greedy algorithm look like? Well, this is some pseudocode for it. Maybe with only 20 minutes to go, I probably don't have time to go through that, but this is a graphical representation of the greedy algorithm. So maybe I'll try to show this. So the idea here is imagine you have a two-dimensional parameter space. So maybe like a bar where you've got two different Young's moduli in the different regions, as a simple example. So, on one axis is the first Young's modulus, the other axis is the second Young's modulus of a different part of the model. So at any different point you choose, you'll get a different solution, right? And what the idea of the greedy method is first to randomly lay down a large set of training samples. So just choose them randomly in this parameter space. And then what you do is you solve the reduced basis model at every point. So at step one, you solve it at every single point. And the nice thing the reduced basis method has is I've already talked about it, a posteriori error indicator. So instead of solving the full order model at every point and doing a POD, what you do is you solve the reduced order model at every point and you evaluate the a posteriori error indicator, which is very fast. It does not depend on the size of big N. It doesn't depend on big N. It's very fast to evaluate. It only depends on little n. So that means you can very quickly evaluate the a posteriori error indicator, every one of these black dots, and you find the one that has the largest error indicator, which is this delta S. That's the notation. If I go back to this slide, this delta S is the notation for the error indicator. So you pick the new point, which is the one that has the largest error indicator associated with it, and then you add that to the basis. So at step 4, we'd already picked these points, and then at step 4, we found this is the new point. Then you see step 5, this is now one of the points in the basis. Like this is one of the snapshots that form the basis. And we do the same loop over all the points again, because the error indicators are updated based on the new basis. And you find now that the new largest point is here, so you pick that one. And the idea is, if you try this in practice, you find very, very quick convergence. In particular, the greedy algorithm converges rapidly. There's been papers that show it has exponential convergence under reasonable assumptions. So you typically reach the tolerance you're interested in with a small reduced basis space. And again, this is just to show there's a lot of mathematics behind the error estimator part of this. And again, I don't have time to go through this, but this is all covered in that review article I alluded to at the beginning. So this is rigorous a posteriori error analysis. It builds a lot on the FEA, the finite element literature on a posteriori error analysis. This kind of the idea of basically having this residual that you compute the dual norm of is basically the same idea you have in the FEA error analysis world. The key difference is that in the RB world, it's actually a little bit nicer in a way, because the so-called truth solution you're trying to compare to is finite dimensional. In a finite element context, your a posteriori error indicators are with respect to an infinite dimensional space, right? For the PDE itself is infinite dimensional, and that makes things more tricky. A lot of things are not fully computable. But in the RB world, because the truth solution you're comparing to is finite dimensional, that makes everything explicitly computable. For example, you can compute a Riesz representation of this residual, and that's fully computable, and you can have an explicit error indicator based on that. So that's one of the nice things, and we use that, at Akselos as part of our error estimator functionality that I referred to earlier. So there's quite a lot here. For those interested, it's a nice topic and closely related to error analysis in the FEA world as well, and builds on that, I would say, and reuses the same ideas, but has the advantage of some things that are not explicitly computable in the infinite dimensional context become explicitly computable, and you have an explicit error bound in these cases. So yeah, that's pretty much all I have time to say on this topic, but hopefully I just plant the seeds that there's a lot of interesting mathematics behind this that makes it a very powerful method. And that's the error indicator that's used here in the greedy algorithm, but it's also used in the online stage when you want to run an analysis, you run a simulation, you want to solve, and you want to know if it's accurate. Well, you can compute an accuracy indicator based on this error estimator framework that's part of the so-called certified reduced basis method literature. Okay, so that's everything I've said so far is sort of summarizing the reduced basis method. And that's a method that's been applied to a wide range of PDEs. As I said, there's hundreds of papers on this topic. Time-dependent, frequency domain, nonlinear, and it's all followed the same framework above, but obviously extended in various directions. In the nonlinear case, you might see literature around hyperreductions such as EIM, discrete EIM, GAPI POD to ensure fast online response. So that's one extra element you need in the nonlinear framework, but that is also well established and part of the literature. But so basically, I would say RB is well established for linear and nonlinear problems. And if you include the EIM, DEM kind of DEIM approaches, that's a key part of the nonlinear framework, then it's a very well established method. But the main limitation of it is that, is the bottom one I'll get to in a second. One limitation is that the solution manifold should be smooth if you expect a low dimensional reduced basis space to be created. So that's going back here. If we have a solution manifold that's chopping all over the place, you can imagine it's going to be very hard to make a low dimensional solution representation of that solution manifold. So a lot of the focus in the RB and reduced order modeling world has been on so-called solutions that are so-called smooth and parameter space, and that's a large fraction of structural analysis problems, for example, fit that mold. I can talk about what we do in Akselos when we have cases that don't fit that mold, but I can get to that later. So that's one kind of fundamental limitation. You have to have a so-called low Kolmogorov end width. That just means you need to have the solution has to be reducible. If it's jumping all over the place, it's basically not reducible, and you can't do any better than just solving it with FEA for every new parameter. But if it is reducible, then creating an efficient reduced basis is a great idea, and that's what we do at Akselos. In all the cases where we can. And then that's one limitation. The other limitation is single domain. So everything I said so far is so-called single domain reduced basis. So that means you just have one reduced basis for the entire model, and that can limit the scale that you can apply the methodology on, and it can also limit the number of parameters, because if you've got too many parameters in your model, it can be very hard to train. You get the so-called curse of dimensionality. It can be very hard to create an efficient reduced basis. So what we do at Akselos is we go to component-based reduced basis, or what we refer commercially to as RBFEA. And again, there's papers on this you can look up if you're interested. So the key idea is we have component interior and interface reduced order models for efficient modeling with many parameters. So we make reduced order models on the component interfaces and on the component interiors. We have automated training based on system level error indicators. So we have error indicators like I was talking about earlier at the system level now, so that they propagate up from the components to the system level, and that will tell you globally if your solution is accurate. And you can enrich further if you ever trigger that it's not accurate enough. And we have training based on individual components and component groups, which means we never have to do a global full order model in order to train the model. So we can train these huge models and solve them with RBFEA and evaluate our accuracy indicator without ever solving the full model with FEA. So it's basically has become a way for us to solve huge structural models that we basically are not feasible in many cases to solve with FEA at all, because you'd have to get some extraordinary amount of computational resources to solve it. But with RBFEA, you just train it based on local groups of components, put them all together, and solve the model, and be confident, and you have confidence in the answer because you have the error indicators that I've talked about. So that's where we've ended up with this methodology, and it's been very powerful. And just to contrast, and there was some I referred earlier to substructuring. Again, people ask me, what's the difference with substructuring? Well, there's a few differences. One, we have parameters, so each component has parameters in it. Another is we have reduced basis on the interior, which is handling the parameters, and we have reduced basis on the interfaces. So reduced basis on the interfaces is key because when you get models like this, you have huge interfaces, and with substructuring, it can be very inefficient with these large interfaces, and you get a dense matrix at the end of the day with substructuring. It can be basically with substructuring, it can end up being about the same speed as just doing standard FEA. Whereas if you have our approach with the reduced order modeling on the interiors and the interfaces, it tends to be 1,000 times faster than FEA. Of course, the nonlinear is a key difference. Substructuring is a linear methodology. So with RBFEA, we have the nonlinear that I talked about earlier, and bringing that into the component-based framework also is a key difference. So quite a lot of differences, but of course it looks similar in the idea of having components. So that's I guess the superficial similarity is we use components. Also, we think that's a great aspect of substructuring, but we take it further in several directions: parameters, reduced order modeling, nonlinear, etc. All right, so this is what a example RBFE solution looks like. So here's a structural model. As I said, this is an offshore ship type structure. With the model, it has more than 100 million degrees of freedom if you solve it with FEA. But with RBFEA, we're able to solve it in 10 seconds, and with the error indicator evaluated as part of those 10 seconds. So we solve it in 10 seconds, even though it's a huge model, and we have guaranteed accuracy through the error indicator. And so at Akselos, we provide this RBFEA framework via a cloud-based high-performance computing framework that includes the training functionality. So you can basically run this training framework I talked about earlier, where you do the sampling of parameters and so on, and create the basis for each component, and create all the interfaces between components, and that all runs on the cloud. And the nice thing about that is each component is trained independently, so it's highly parallelizable on the cloud. So you can have hundreds or thousands of cores running, training the model, and then when you run the solve, it's also leveraging parallelism and so on the cloud. But of course, the speed up we're bringing is not at all based on many compute, using many, parallelizing the compute. The speed up is algorithmic. It's based on the fact that we've reduced from big N to little n through the reduced basis approach. And then, the cloud-based framework is obviously just an extra efficiency on top of that, because of course, a lot of this is parallelizable. When you've got many components, you can assign a subset of the components to each processor. The training is also parallelizable, as I've said. We also provide FEA on the cloud. So RBFEA is built on FEA. So we, of course, have an FEA as part of our platform. We have CFD for other applications. We don't have RBCFD at this stage, but we have full order CFD, which we bring into some models, and other kinds of scientific machine learning we've brought in for various applications. But what we're most known for is the RBFEA. I've only got 5 minutes left, so I've got plenty of examples, but one thing I'll just show quickly is nonlinear. So as I've said, we can do nonlinear with RBFEA, but if you have nonlinear that's not smooth, so like plasticity, for example, is a good example of what I would consider a non-smooth solution manifold, because as you change the load, the plastic front jumps, right? It can jump from one quadrant point to the next, and that would be a non-smooth solution manifold. So in those cases, what we do is, we say if it's a smooth nonlinearity, like geometric nonlinearity, or creep tends to be quite smooth, or heat transfer, where the material properties depend on the current temperature, that's nonlinear. These are good cases for nonlinear RB. In cases of non-smooth nonlinearities, you would probably have a hard time training it with RB. You can try, and we do have implementations of that, and we use it in some cases. But in other cases, if it's really is non-smooth, then you basically can't do any better than just solving it with FEA. So what we do then is we have what we call the hybrid solver. And that means what you can do is you can combine FEA and RBFEA in one model. And this is just showing how we do the coupling. You basically have a standard FEA model, so standard residual for the FEA region, and then the residual for the RBFEA region, and you couple them together with this coupling matrix. And you end up with a Newton method for the fully coupled system, and the implementation is standard at that point. But you can basically, what you can do is you can have a huge model, and you can designate part of it to be FEA because you have non-smooth nonlinearities in those regions, like a local failure, like a buckling or whatever. But you can do a global load case and then transfer to the local nonlinearities with FEA and solve it with one fully coupled method. And then here, you wouldn't get necessarily 1000x speed up because you're not using RB everywhere, but you might get 900x speed up or something if the FEA region is small. But of course, as you make the FEA region bigger and bigger, you start to look like you're solving the model with FEA. So it's kind of like, I think of the hybrid solver as like a slider bar between FEA and RBFEA. If you put the slider bar at one extreme, you get FEA. If you put it at the other extreme, you get RBFEA, but you're free to put it somewhere in the middle, ideally somewhere close to the RBFEA side, so you're getting good speed up because of these localized nonlinearities, but really you're free to put it wherever you want. And here's another example where we've got a bearing with contact and plasticity at the contact points, and so we have these little components here. These are FEA components, and the rest of it is RBFEA. So again, you're getting the speed up elsewhere due to RBFEA, and you're getting the localized FEA regions handling the non-smooth nonlinearities. And then I've just got a whole bunch of examples, which I don't think I've got too much time to go through. So Eleni, how about...
Yes, but don't feel too much pressured. I think for our students in particular, they would like to see some real use cases. So if you want to just, only namely at least refer to them, that's also okay.
Sure, yeah. So, okay, I can run through examples. So the first one is this is called an FPSO. This, I've already referred to this a few times. This is a huge structure, 300,000 tons. And again, we're providing RBFEA modeling of this. And again, to make it industrially applicable, you can't just provide a model, you have to do all kinds of stuff. So this is what we've developed, all these different things, incorporating inspections, configuring topside weights. So topside is all this stuff on top of the hull. configuring all the static loads, like the different ballast and cargo loads, hydrodynamic loads, which is the wave loads, and meshing of all the hotspots. So with fatigue hotspots, there's industry standards about how you do the meshing. So we have T by T meshing at the fatigue hotspots, all in one model, which is unheard of. People traditionally make one coarse global model and then they zoom in and make locally fine models for the fatigue hotspots. But because of our BFEA, we can have one model, high fidelity everywhere, including all fatigue regions, and analyzed simultaneously. We have various add-ons like the riser porches and strength analysis and fatigue analysis and fatigue screening. So these are all the different things we've developed as we've brought this solution to our customers. And the point is, again, we provide dashboards which provide an updated, automatically updated view of the asset, so they can ensure to operate it in a smart way. Here is bringing in inspection data. So what they do is they go on the vessel. As part of regulations, they have to do thickness measurements, so ultrasonic thickness measurements. They go on the vessel, they collect thickness measurements, which is basically measuring corrosion. And then they say, well, what do we do with that? Well, traditionally, thickness measurements were just checked against a rule. The rule said, is your corrosion more than 20%? If yes, that's you need to do some repairs. If no, then you're okay. Like a very simple check like that. What we do is we bring the inspection data into the model and we rerun all the load cases and run the code checks and give an output. So this is showing how we can incorporate the thickness data into the model, and then we can, for example, generate plots showing the updated thickness measurements, and we can, of course, run all these things like I was talking about here, like fatigue analysis, telling you if the updated thickness measurements are telling you there's some issues in different regions of the structure, and then we can auto-generate outputs. So what we generate here is like a plan view of different frames in the hull, and superimposed on that are locations of fatigue hotspots. So this is critical information for them when they do inspection planning and risk-based inspection. They know where the fatigue hotspots are, and they can make sure to prioritize those locations. And you can see in the giant hull, we can pick out like 20 critical hotspots out of 100,000 possible hotspots and tell them where to focus their time and energy, and also be sure that they're really tracking the structural integrity of these assets. So this is about asset life extension. Making sure your asset that you're tracking the current state of your asset and making sure it's satisfying all requirements for continued operation. And this is about reducing OPEX, so making sure you're efficiently doing inspections and reducing risk. Of course, anytime you have any kind of structural issue like an impact, in the field, things will happen. There'll be accidents, there'll be collisions. A tanker can bump into the side of this giant ship and you get damage. Well, of course, with the model in place, you can incorporate new components. You can do a component swap that incorporates damage and rerun the whole analysis with the newly modeled damage incorporated. So this is like being ready for any eventuality with the model already prepared for any kind of analysis. And this is a typical kind of dashboard showing fatigue accumulation and telling you the status of different parts of the hull, allowing the operator to focus on different areas of interest. And this is a reactor digital twin. So this is a high pressure, high temperature system where, again, in this case, they're worried about what's called hydrogen embrittlement. So when you're cooling it down and heating it up, you can get hydrogen entering into the steel, causing hydrogen embrittlement, which can be a catastrophic failure. So there's ways of managing that. They call it minimum pressurized temperature curves, but they had no way of doing that in operation. So what we provide is a fast analysis tool that runs in sync with the real asset, incorporating sensor data and giving them a live feed of the current state of the asset, ensuring they can avoid hydrogen embrittlement. And that's key value. It enables them to do startup and shutdown faster, which brings very large value because reduces downtime of assets. This is floating wind. So this is an area we've been working in, which is floating offshore wind. So you're familiar with wind turbines onshore and probably offshore turbines where they're on a fixed bottom structure. And a new development in the last several years is floating offshore wind. So what you do is you put it on a floating structure. And the key value of that is you can put it further out to sea or put it into locations where the water is deep. And that's a large portion of the ocean is too deep for fixed bottom offshore wind. So there's a lot of interest in floating floating offshore wind turbines. And again, there's a lot of structural challenges with this because it's much more complex. You have to, you got a floating structure, you got waves, it's moving around all over the place, and you've got a lot of complex, hull type structures to manage. So we basically use the same kind of solution that I showed earlier for the ship structures, but applied to floating wind. Although there's differences in the fatigue analysis. This has to be time domain because the turbines have nonlinear behavior. You can't do it in a frequency domain type of analysis, whereas ship structures you traditionally do in a frequency domain analysis, which simplifies some things. So this is more computationally intensive because of the fact it has to be in time domain. And again, that's a great fit for RBFEA, where we can solve these complex structures with very refined meshes in fatigue hotspots efficiently in the time domain. And just to get a sense of the scale, I mean, this is tiny compared to the ships we were talking about, but this platform might look small, but if you put it in, compared to buildings in Copenhagen, you see that these are giant structures. And you can imagine inside these tubes is very complex stiffener structures, and you need to model the whole thing in order to do an honest structural integrity analysis. Here's another, process equipment type of example where we see, again, dashboards, tracking the asset, and you see these kinds of jumps in fatigue utilization. That helps them figure out something bad happened on this day. Let's not do that again. So, similar sort of themes over and over where we track assets in operation and help the operator do a better job of managing how the asset is being utilized and avoiding inefficiency and identifying any problem areas ahead of time. And another example is incorporating inspection data. So you can see one customer had an issue where they collected very high fidelity inspection data, but they weren't able to do much with it because they couldn't analyze with that level of fidelity that actually would be required to actually incorporate this detailed inspection data. So what we did is we showed, again, with an RBFEA model, we can incorporate highly detailed inspection plans. Here's the inspection data, not inspection plans, it's inspection data, laser scan data. We incorporated this kind of laser scan data on an actual structural model, and then we run the analysis. So again, RBFEA, because you can have very high fidelity modeling, we can have very refined meshes and basically directly incorporate this kind of inspection data into the model and run the analysis and do the structural integrity analysis based on the as-is state of the model, as-is state of the asset as it is imported into the model. This is one with creep. So I mentioned, RBFEA with creep. This is pipes. Again, high temperature, high pressure. You get creep, complicated nonlinear phenomena. And this is a huge pipe structure, more than 100 million degrees of freedom when it's fully modeled. And we model the whole thing. And this is very, very critical asset that you can see all the complicated pipe structure with creep in it. It's just another example. So, and then here's a lifting frame type, crane type structure where, again, a customer used our solution under the hood to make a dashboard with various kinds of metrics on it, analyzing the structural integrity during operations. And here's a mining example. So this is called a reclaimer, where in mining companies, they reclaim the soil that's been dug up. And again, dashboards are the main outcome. This was an academic example we worked on with Professor Wilcox in UT Austin, who had an instrumented aircraft. And again, we provided a structural, this is like a little UAV type aircraft. And the idea was to have a digital twin which could run during operations. So we wrote some papers on this, recently with them, and was well received in the literature. Where the idea is you could have a digital twin operating during flight and informing changes in the flight path based on what's being detected by the digital twin. If damage is detected, then the thing might be under attack, and you might need to change your flight path to get home safely, for example. All right, so that's the end. I'll just give my conclusions. So Akselos developed RBFEA as a powerful tool for large-scale industrial digital twins. RBFEA is a component-based, physics-based, reduced order model approach, or relatedly scientific machine learning approach, because we train a low-dimensional representation, a reduced basis representation of the solution manifold for each component and each interface. RBFEA enables error indicators, like I've talked about quite a lot, which means we can automatically run training guided by indicators, like, for example, the greedy algorithm, but similarly at the system level. and it gives reliable solutions in the online phase. Online means when the solution is deployed. It gives reliable solutions when the model is deployed, because we're not just running the solve, we're also getting an accuracy analysis as part of the solve. And Akselos provides a range of simulation tools, RBFEA, but also other stuff when our customers need it, because we have a philosophy that we want the right tool for the job available for any case. But RBFEA obviously is our key tool that I've talked about in this presentation. All right, thank you.
Thank you very much for the very nice presentation. And I'm also very happy to see, those examples in particular, because they can be very compelling, I think, also for our students to understand that there's practical use or exploitation of these kinds of schemes. I would like to open the floor for questions. And with this, just to mention that anyone in the audience could just raise their hand, and I'm happy to offer them their floor, or unmute yourselves. I see Paolo has done so already, so you can go ahead.
Oh, yeah. Thanks for the very interesting and broad talk. I'm just curious about the interface reduction, because I have the impression that really your giant structures are really divided into a lot of subdomains. And as you mentioned, if you don't do the interface reduction, the method is simply inefficient. You get large matrices which are full. Could you disclose something? Could you elaborate a bit on the techniques that you use to interface reduction?
I mean, it's reduced on modeling, the same kind of stuff. Just like I said, we do analysis on groups of components, and when you do that, you're getting data on the interface. There's papers by Padera and collaborators on what they call optimal modes. So that's basically a way to generate optimal interface degrees of freedom, reduced degrees of freedom under certain assumptions. So there's literature out there. It's probably the best thing I could do is point you to that. Optimal modes is one approach. But you can get the idea that anytime that's why you need to have groups in the component-based training world. You have to have groups of components, because they have to talk to each other, and that's the key idea. Once you do that, that's the essence of it.
Well, maybe relating to this, would the assembly just be sort of a superposition, or now that you have more nonlinear interconnections, you have to have another type of function that does the assembly?
You're talking about how we do the assembly?
Well, you have the components, and then you have to put them together, right? And would that just be superposition, or now in the nonlinear case and these complex interactions, you need something?
The way we do it is we treat interface. We make interfaces degrees of freedom, right? So you just like in nonlinear FEA, you have degrees of freedom on element boundaries. That's the same kind of idea. You can do it different ways. There are many approaches where people do mortar type methods for coupling. There's many ways to couple components, and mortar methods are reasonable as well, but we tend to use more like interface degrees of freedom.
I interrupted Paolo, so I'll give him the floor to finish his question.
No, I mean, it's fine. I mean, because I've been working on interface reduction in the past myself. We're more relying on, they say, eigenvalues at the interface, eigenvalues and eigenvectors, rather than looking at data. But I understand that you really group components, and you're trying to train the interface as well.
Yeah, because you typically know, again, in the digital twin context, which components are next to which other components. And so you want to leverage that information. I mean, I think that's the key insight when you get to industrial problems is you need to focus on the asset you're trying to deal with. Because when we started out trying to be extremely generic, and things get very inefficient very quickly, because as you try to be too generic, you lose a lot of the advantages of a reduced basis. But if you focus in on the asset you're trying to deal with, you can get a lot of efficiency. But that does mean you say, okay, well, I'm not going to pair this component with every other component. Then you get a combinatorial explosion of data. But if you pair it with the ones that it actually needs to be paired with, you get a good focusing of a basis.
Thank you. Yeah, makes sense.
The next would be Boja. You've raised your hand. Go ahead.
Yes, thank you. Thank you, Elaine. Thank you, David. I want to ask about the integration with the data that is monitored live. Structural integrity data from vibration measurements is often space-wise. I mean, involves perhaps the whole model. Monitoring data from strain gauges may be very localized.
Yes.
How do you organize? I mean, I see it could go through interfaces. possibly, but how do you organize this kind of merging of the data that comes in from the field with the model? What is the interface structure, and how do you deal with this dimension?
Yeah, it's a great question, and I mean, we would love to collaborate with the experts at ETH on this kind of thing. These data assimilation questions are not simple, right? So, one thing is we developed a forward solver. Like most of what I talked about today was a forward solver. Like you set the parameter, you solve, and that's that's a lot of times what we're doing. But yeah, you're right. Sometimes you need to do more like an inverse problem where you measure. You've got measurements from the field, and you need to figure out how to fit those. So we've explored different things in the past. I think you're right. Strain gauges are very localized. Other kinds. A lot of what we do is temperature sensors, so that tends to be quite temperature is very smooth, right? So that tends to be one that's quite nice. Strain gauges and vibration. We'd love to collaborate, I think, with this kind of audience on cool things to do in that area. And I'm sure there's a lot more we could do. We try to be very sophisticated on our forward solver and very simple on everything else, right? And if we can do more sophisticated things, we'd be very interested in that. But I think that would be an area where collaboration would help drive things forward. But just to give you a flavor, what I mean by simple is we just treat it like an optimization problem. You have a strain gauge. You have your strain gauge measurement, and you have your model, which has a strain output at a particular point, and there's a mismatch between the two. And you've got maybe 10 strain gauges on your structure. You can just say, well, I need to change my parameters until my mismatch is minimized, right? So that's one simple thing. If you've got a fast parametric solver, you can run an optimization loop essentially, which will update your parameters until you minimize the mismatch. So that's one approach that that we have deployed in the past. But we don't claim to be doing the best stuff on that front. And I've said many times, the sensor world is something we'd love to collaborate with people more on.
Great to hear. Also for me, we specialize in these inverse problems, let's say, also in real time, because many times what you explain to the solution of a conventional optimization problem really means an offline method. You need to have your batch of data and somehow create your fitness function, but there's ways to also do it in real time or as data.
Well, I'm very glad to connect with this audience then, because there's definitely some stuff we can do there. And yeah, it comes up with our industrial customers. It comes up for sure. I mean, we have strain gauge data on ships. We have strain gauge data on platforms. We have vibration questions coming up left and right. And we just kind of do something to get something working, but I'm sure we could do more.
Again, I interrupted Bozo. So
thank you very much. I mean, this is something that I'd like to know about and keep in mind. And yes, if we can help, that would be really great. For us, it would be quite interesting to figure out if there is a way to monitor the effects of climate change over a period on some kind of future performance of the system. Some years, not too far in the future, but some years from now.
Good.
Are there further questions for our speaker? Again, you can raise your hand or unmute. We're already Kostas. Yes, go ahead. Maybe I also should explain that Kostas is the teaching assistant for our finite elements class. So, and also works on parametric reduced order models for his doctorate. So I give him the floor.
Thanks, Eleni. Hi, David. Thanks for the very interesting presentation. I was wondering, with respect to the pressure vessel example that you showed, that you incorporated the data from I was wondering, because you construct the digital twin with a certain assumption on the parameters. What are these parameters? What do they represent? But then you incorporate some data that comes from different modalities, right? You showed this camera data. Do you translate those to the initial parametric assumptions you have, or a priori your parametric assumptions are a bit flexible so that you can leave room for incorporating different modalities of data later?
That's a great question. I mean, in cases of simple data that we're collecting. So, for example, on ship hulls, when they collect thickness measurements, they don't do point by point. They do this entire panel has a thickness reduction of 3% because they take a few measurements and they have some averaging out. So you could imagine a priori saying, well, this thickness in each panel can vary by 10%, and you train your space with that knowledge, right? And that would define your parametric manifold, and you train on that. And then any new data presumably fits within that, because historically you can expect that, and that's fine. The pitting case is totally different because it's super high fidelity data. There's no way you can define parameters. You'd have to define a different parameter at every node or something, right? Which is millions of parameters. It's not feasible. So what we do, and that's more like a case where it's more like using the RBFEA capabilities of solving large scale models, not so much parametric. So it's not so much like we don't want to really avoid training in that case. If you incorporate new data, then we will probably, and you run the solve, it'll detect that it needs an enrichment of the basis, because the new data is outside anything you've trained, because of course there was no way we could have anticipated that. And then it'll just trigger an enrichment. But it's still, basically the idea is, well, that's a model that's so detailed, you would have a lot of trouble solving it with standard FEA. So that we're just using this as a way to solve it with solve a large scale problem efficiently with RBFEA. So I think there's two different ways we end up using RBFEA. One is kind of non-parametrically as a scalable solver, because you can train localized components, put them together, and get an efficient global solve. So that's really just a scale, almost like a domain decomposition solver. And the other way is when you can, like you're saying, when you can anticipate parametric variations, you can build those into the training, and then new evaluations will not trigger a new training because you've anticipated them in your training. So hopefully that gives a reasonable answer to your question.
No, exactly. That's exactly, because this is what we were working on, Eleni, this trigger that we mentioned, because it is acceptable. You cannot capture everything. So as you said, you need to trigger this retraining. That's great.
A similar thing comes up with us in defects. So if you've got a large structure, you cannot anticipate where a crack will be, right? If they go around and they find, oh, there's a crack here and it's 2 inches long and it's curved like this, you can't parameterize that because you have no idea where it's going to be. What we do instead is we say, okay, stick the new component in with the crack and solve the global model. And if you have to do training, you only have to do training on that component, or maybe the component and its neighbor. Similarly with the scan thing, well, they scan a part of it at a time. So you put one new component in with the new scan data, and if there's new enrichment needed, it's only needed locally. So it's sort of the scalable solver side of it, as opposed to the anticipating parameter side of it. But they all fit together, right? I mean, it's all kind of part of the same idea.
Indeed, this modularity is very helpful. Okay, thank you very much.
I don't see further question. Maybe I can ask a last one. For me, we're also dealing with this issue of creating dependencies on parameters. And even though, we hope for the manifold to be smooth, interpolation between parameters that were used to create snapshots is not always trivial. And it's not like we have often a functional dependence on our basis on these parameters. How do you cope with this problem?
I mean, I think, what kind of methodology? You're not using I guess we might be using a different methodology. We're using kind of vanilla RB method, where we just construct the basis and we, as I said, put it in the FEA formulation. So there's no,
but wouldn't it depend, for example, when you have your basis, you create it for different snapshots, right? And then you have a new parameter set, which is not perhaps part of the initial snapshots, because you want to create.
So you're talking about that's where the enrichment comes in.
In that case, yeah.
So what we do there was, that would be detected as a high error indicator. That's the whole point of it. And then it will say, this new parameter that we tried to solve is not accurately represented, but we detect that. And what we do is it'll auto trigger on the cloud enrichment, and basically it'll run new FEA.
It will run and produce the new basis.
For the customer's point of view, they don't see that. They just see that they get the answer, and they don't care about all that stuff. They just see their dashboard being updated when it needs to be updated. And
in our case, we tried to tackle it by trying to create an interpolation scheme that's non-linear. Maybe I'll send you some information.
Yeah, okay. I mean, that's what comes up. Yeah, so on one of my slides where I was talking about the solution manifold, I said, I didn't go into detail, but I said some other methods try to approximate the solution manifold with a nonlinear approximation. This is what the neural network approach is as well, right? That's a nonlinear approximation to the solution manifold. The reduced basis is a linear approximation to the solution manifold, which of course is similar to an FEA type of thing. You have a linear approximation to your space, and then you just find the optimal solution in that space. So it really is an extension of the FEA approach, where you're not trying to do anything other than have a vector space, right? You're approximating in a vector space. It's supposed to obviously surround in some way that solution manifold. Obviously, you can be even more efficient if you have a nonlinear approximator to the solution manifold. A case where this comes up is transport. Like if you got to transport, suppose you just want to transport a bubble to the right, you try to make a reduced basis space for that, it's going to be hopeless, because every time it moves one element over, you need a new basis function, right? So that's what we mean by non-smooth. That's a non-smooth manifold that wouldn't be well suited to RBFEA. But our structural problems are not typically like that, unless you happen to be doing one that is like that. But many times it's not like that, and it works really well. But we are exploring machine learning type approaches, because the nonlinear approximation property can be very powerful in cases where you need it. And I think that might be kind of what, as you say, a nonlinear approximation of the manifold, that's a powerful idea, but that's not what I'd call the vanilla reduced basis method does.
So we probably exceeded the time, and we took more of your time. I hope it has been okay also for you. But I would like to take the chance to thank you very much for this great seminar. Really very nice work, and we'll try to follow up also, because we're excited to possibly collaborate. So I think we'll have more.
Yeah, it's great. I'd love to connect more. And just for everybody's information, we have an office in Lausanne, so not far from you all. But yeah,
only
nice to meet you.
2.5 hours from Zurich, indeed. I'm just going to ask the students who wish to discuss with Kostas on their project to stay in this room. For everyone else, thank you for logging in, and see you soon.
All right, thank you.
Thank you. Bye.